We're going to start chapter 16, which talks about probability in the models. And guess what? We got a test on Friday.
What the?
So, first thing with probability in models, we'll talk about Bernoulli Trials. To qualify to be a Bernoulli trial, it needs these conditions. That there are only two possible outcomes, success or failure. The probability of success is the same for every trial. So like flipping a coin, doesn't matter if the last trial was heads, it doesn't affect my trial I'm doing now. And that the trials are independent. Now there is something called a 10% condition. If the trials are not independent, it is still okay to proceed as long as we randomly select fewer than 10% of the population. Notice this is population. So we want to take a fewer than less than 10% sample size of that population. Then we can proceed. Otherwise, as long as it's independent, it's okay. So these things need to be met in order to be considered a Bernoulli trial. Let's look. Do these situations involve Bernoullis? We roll 50 dice to find the distribution of the number of spots on the faces. Is that a Bernoulli trial? We roll 50 dice to find the distribution of the number of spots on the faces. Which of these does it fail? Which of these fails with rolling the dice? Yeah, two possibilities, right? Sorry, I was mute. Two possibilities. So we know rolling dice has about 6 possibilities. And if you use one of those other kind of dice, this could have a lot more than that. Next, how likely is it that a group of 120, the majority may have type A blood, given that type A is found 43% of the population? Is this a Bernoulli trial? Trying to find how likely is it that a group of 120, that the majority may have type A blood. Does this meet all 3 conditions? I'll tell you, we're so excited. This is so fun already. Look at the conditions. All of these need to be met. Does it meet all those conditions?
Yes.
Yes. Because, first one, only 2 possible outcomes. Well, you're either type A or you're not. Type A will be a success, and any other type is a failure. Next, probability of success is the same every trial. So yeah, the likelihood we pick also works with trials are independent. Each person is independent. Just because you have type A doesn't mean he might have, well, unless you're twins or brothers and sisters. But let's assume that that's not the case. Let's assume they're independent, right? 3, we deal 7 cards from a deck and get all hearts. How likely is that? Is that a Bernoulli trial?
No.
Why?
Because the chances aren't the same every time.
Very good. It fails this one, right? Probability of success is the same on every trial. It is not the same. If I take a card out, then it increases the probability of other cards and decreases the likelihood of others. So, number 4, we wish to predict the outcome of a vote on a school budget and pull 500 of the 3,000 likely votes to see how many favors the proposed budget. Is this a Bernoulli trial?
I don't know.
No.
We wish to predict the outcome of a vote on a school budget and pull 500 of the 3,000 likely votes to see how many favors the proposed budget.
I don't know.
Are there only 2 possible outcomes? They want to look at the budget. I'm guessing you're either voting yes or a no, right?
Yeah.
Yeah.
Probability of success is the same for every trial. And is it independent? Are votes independent?
Yes.
I would say so. And does that fit the probability of success is the same for every trial? No. Oh, no, the trials are not independent. So, kind of iffy whether or not it's independent. I'm not seeing why it wouldn't be, but maybe because it doesn't say the word random. Number 5, a company realizes that about 10% of its packages are not being sealed properly. In a case of 24, is it likely that more than 3 are unused? Is this a Bernoulli trial? Yes. There are only 2 outcomes. More than 3 or not. And they look to be independent, and each trial doesn't affect the other. Okay, so those are Bernoulli trials. Now let's look at geometric probability model. So the big takeaway for today is how long would it take to achieve the first success in a series of Bernoulli trials? So we want to know, when am I going to get my first yes? Or when am I going to get my first whatever I'm looking for? The equation looks like this, where P is the probability of success and Q is the probability of failure. So notice, once I have my probability of success, I want to subtract it by 1. That's going to give me my probability of failure, Q. Capital X is the number of trials until the first success occurs. So that is my capital letter expected value. And it looks like this, Q to the X minus 1 power times P, where my expected value is 1 over P. And here's how you find your standard deviation with geometric probability. Now note, you're not expected to memorize this. There is a calculator trick to help you calculate this right here. But note, you will, I think, have to memorize how to find the expected value of a geometric probability. 1 over P, where P is your probability of success. Let's look at our first example. Postini is a global company specializing in communication security. The company monitors over 1 billion internet messages per day and recently reported that 91% of emails are spam. Let's assume that your email is typical, 91% of your email is spam. We'll also assume that you aren't using a spam filter, so every message gets placed into your inbox, and also each message is independent. So we're basically assuming it is a Bernoulli trial. When you first check your email in the morning, about how many spam emails should you expect to have? I'm not sure what that word is supposed to be.
Yeah.
How many emails should you expect to have that are spam when you first check it? So what is my expected value? My expected value is 1 over P, where P is where my success is actually going to be a good email, right? So a good email is 0.09. That's my percent chance of getting an email I actually want. And my failure, Q, is going to be that 0.91. So let's go with that. A success is a good email and a failure is spam. Okay? So, using this, where my expected value is 1 over P, how many emails should I expect to have that are spam? So it equals 1 over 0.09, which gives me 11.1. 11.1 emails. So, yeah, there you go. Sorry about this. I feel like I'm missing a sentence somewhere. Type this very quickly. All right, so here's how you expect it to find the expected value with geometric probability. Again, just 1 over P. Now, what is the probability that the fourth message in your inbox is on it that, okay. Fourth message in your inbox is the first on that isn't spam.
This is why you're not an
Isn't
English
one that
teacher.
isn't?
What?
Isn't one? Is the first one?
Oh, first one. Here we go. That isn't spam. What's the probability that the fourth message in your inbox isn't spam? Okay, so if I were to break this out into a tree, I know I either have good or bad, right? So spam gives me 0.91 and not spam is 0.09. Then I get another email and I'm breaking that out to spam, not spam, and I'm breaking that out. So I have this tree and I have to do some multiplication. But there is an easier method to find this probability. I know that my first one that is good, that means how many are spam out of 4? 3, right? The first 3 are bad. So I need to multiply the probability of bad, 0.91, times 3. So let's just call that the third power, until I get to one that is good, which is 0.09. Right? The fact that it goes with the tree, I know fourth one is going to be good, which means my other three are bad. So bad, bad, bad times one good. So what is that? 0.91 to the third power times 0.9. Gives me the probability of 0.0678. So roughly 6.8% chance that my first good message is the fourth one. Now to do this in the calculator, let me move this here. Make sure you pay very close attention to this. Calculator has a geometric probability feature in it. You're going to find it in distribution. So second vars, everybody probably should want to do this with me. So right here ahead, above vars, variance is distribution. So second vars gets you to this distribution. Go all the way down till you see geometric PDF. Geometric, bio, no, not bio, geometric. All the way down. There we go.
E?
Mine, yours says E, mine says F. I got a different format. There you go. Geometric PDF. Hit enter. You're going to enter your p-value. So my success rate of getting a good email is 0.09. You're going to enter your x value. What number do you want that first success to be? In my case, it asks for 4. So my x value, I'm going to put 4. And I'm going to hit enter, and then enter again. And what's the probability of the fourth email being a good one?
That's cool.
Like so. So again, I'm going to upload these notes here in a minute. One more example. Actually, we have a couple more. You are opening boxes of cereal one at a time looking for your favorite sports player's card, which is in about 15% of the boxes. You want to know how many boxes you might have to open in order to find the picture. You run a simulation consisting of 1,000 trials, and each trial you open cereal boxes one at a time until the card is found. Calculate the actual or geometric probability model. So I have outcomes here. First, I need to define what is my probability for success. What is my P? 15% or 0.15. You want to make sure you put the decimal in the calculator. Now, to find the first outcome, I need to take my calculator. This is going to be my p-value, and my x value is going to be each of these on the top, right? So my outcome is going to be my x. So one by one, I'm going to go down and plug in these numbers. So what is the probability that the first box I open gives me the card? Well, you should know that's 15%, right? But for demonstration, what you can also do is do second enter, instead of having to go through all that again. To pull up your, the last thing you did on the calculator, that's at 15. First one is 0.15. So 0.15. I'll just stay over here. Next, what's the probability that I find the card on my second box? After the first box failed, what's the probability of the second box? Here, 0.1275. 0.1275. So about 13%. Next, again, second enter. Change that to 3. So the first 2 boxes failed. What's the chance of that third box being the card? So about 11%. So 0.10, was it 8?
8.
Yeah, say 3. Now go ahead and fill in for 4, 5, 6, 7, 8 and see if you can figure out 9 or more. Now, how do you find this number right here? If you plug in 9 in your calculator, that gives you 9, where 8 failed previously, but doesn't give you 9 or more. because that's looking for 9, 10, 11, 12, 13, all the way to infinity. How in the world do you think you could find that number? I do know this value, right? So if I were to add up all these numbers together, 0.1 plus 1.28, nope, 0.128 plus 1.08 plus 1.92 plus 0.78 plus 0.67 plus 0.57. Let's have made a typo. That is 0.728. So the probability of me finding the card between 1 and 8 is about a 72.8% chance. So how do I turn that into 9 or more?
Subtract that.
Very good. By 1. So the probability of this happening, me finding my card between this range, is 72.8% chance. What's the probability of the rest of it? Well, we know probability has to equal 1 total. So subtract 1. And you get what? 0.272. So again, how do you find 9 or more, or let's say 8 or more? Add 1 through 7, subtract from 1. Does that make sense? All right. Last question. A basketball player has made 75% of his foul shots during the season. Assuming the shots are independent, find the probability that in tonight's game he does the following. He misses for the first time on his 4th attempt, and B, he makes his first basket on his 7th shot. So note, what is my probability for success?
0.75.
Yeah, 0.75. What is my probability for failure? 0.25. Now use these numbers to solve A and B. All right, a way to do this by hand, if you want to do it by hand, is I have misses for the first time, which means he was making them, right? Probability of making them is 0.75. How many times did he make the shot before he missed? 3. So that's 0.75 to the 3rd power times when he finally missed, which is 25% chance. And that equals, what'd you get? Well, it equals the same thing if you would have went in your calculator and did the geometric. What am I going to put here for P? 25, right? Because I'm looking at what's the first time when he missed. And he took on the 4th attempt. Did you get 10.5? So, I'll just make a percentage. So about 10.5%. And then makes his first basket on his 7th shot. So he missed how many before he made it? 6. So that's to the 6th power. So now he finally made it, which was 75% chance. Or in the calculator, what would this look like? What did I put here for my P probability? 75, and what number did I put here? 6, right? Was it 6? Oh, sorry, 7. Seventh. So scientific notation. So I got 3 zeros. 0.000. Was that a 1? 1/8. 1/8. So roughly 0.018% chance of it taking his 7th shot for him to finally make one. Must be a very good free throw shooter. Okay. Hypothetically, the power of geometric probability is so that you can start doing things like this. What is this telling me? This is calculating the probability of what happening? What does this mean? make what?
Made
He made 3, and then he
three.
mixed 6, and then he
Made
made 2. Yep. What is the probability that his first 3 he made, then he mixed 6 in a row, and then he made 2? Again, this is kind of just following that distribution tree.